Let's go to question number 5. We want to derive an equation for the instantaneous acceleration of the car as a function of time. And we want to identify the acceleration of the car when t equals 0 and the asymptote of the function as t goes to infinity. So let's remember the formula for the velocity is a times 1 minus e to the power of minus small t over capital T. Let's expand the brackets. The acceleration is going to be the first derivative of the velocity is dv over dt. So that's going to be the derivative of a minus a times e to the power of minus t over capital T, the derivative of that. The derivative of the first function minus the derivative of the second function. This is a constant, so the derivative of this constant function is going to be 0. Then we have minus a does not depend on t is a constant, so it can be moved outside the derivative, times e to the power of minus t over capital T, derivative of that. It's going to be minus a times the derivative of the exponential is the exponential function, and because this variable is scaled here, is going to be minus t over capital T, derivative of that. So it's going to be minus a times the derivative of t is going to be 1 over this constant t, 1 over t with a minus 1 over t. So it's going to multiply this one, minus 1 over t times minus a times e to the power of minus small t over capital T. Minus times minus turns into a plus, a over t times e to the power of minus small t over capital T. So my acceleration a of t is capital A over capital T times e to the minus small t over capital T for t bigger than or equal to 0. That's my acceleration, and for t equals 0 I can find what is the value of the acceleration. It's going to be a over t e to the minus 0 over capital T. So a of 0 is going to be capital A over capital T, meters per second squared. That is going to be the acceleration of the car for t equals 0. Now the other question is to find the asymptote of this function as t goes to infinity. Let's take the limit of a of t as t goes to infinity. It's going to be the limit as t goes to infinity, the variable t, of my function a over t times e to the minus small t over capital T. The constant is not affecting the limit, so it's going to be a over t times the limit as t goes to infinity e to the power of minus small t over capital T. This is exponentially decaying function, so when t grows to infinity, this whole thing goes to 0. So it's going to be a over capital T times 0, so that gives me 0. And the limit as t goes to infinity of the acceleration a of t is 0. So the axis t, the time axis, is an asymptote of the acceleration A of t. Okay, so the asymptote is of the form yt equals 0. That is the asymptote. And of course I have the formula for the acceleration written here. The value when you when you plug t equals 0, you find the acceleration for t equals 0 is a over t meters per second squared, and then you find the asymptote, which is the horizontal axis. The time axis is the asymptote of the function.